Hello everyone, my name is Jim Webber and I am Chief Scientist at Neo4j, the graph company. Now, when I last worked in India, hello Bangalore, you crazy beautiful garden city, India was already a tech powerhouse for doing heavy lifting, predominantly for markets in the West. But what's amazing to me over the last decade is that homegrown innovation on the subcontinent has accelerated so much. It's simply amazing. So it's a real pleasure and privilege for me to be back with you, the tech community on the subcontinent. My only lament is that we still can't do this in person. I would love to have been there with you in person, enjoying the wonderful hospitality of the subcontinent. Instead, we'll do this remotely and we'll hope to do it in person again in the future. So in this keynote, we're going to look back at data trends long term. And we're going to have a think about how we've entered a new era of not just collecting data, funneling data into lakes or what have you, but connecting data and taking, growing and harnessing value from that connected data. So if we think about the framework that we're going to use to support our narrative, there's a kind of evolution of data processing that's happened in our lifetimes, where we have gathered data as distinct data points, and we have tried to enrich that data somehow to derive information from it and to connect facts in that information together to provide knowledge. And once we have knowledge, we've been able to try to extract facets of that knowledge for insight, and indeed, at the logical extent, to connect paths through that knowledge to provide what might amount to wisdom. Now, our universe, our world, didn't start off that way. In fact, back in the day, when data became a discipline in the era of relational databases, when our systems were being formed, the data that we had wasn't particularly interesting, actually. It was pretty uniformly shaped, and it was pretty predictable. Data was square or rectangular. We had payroll, and my payroll entry and your payroll entry were the same, and my bank account or my fuel bill or my car insurance, they were all the same as all of my neighbours, and indeed probably people all across the planet. And they could all be quite happily represented in tables. We hadn't thought about personalising this data yet. It was a one-size-fits-all model where we, the people or the objects in our real world, were decomposed to suit the database. And in fact, when I grew up, he was the Prime Minister when I grew up here in the UK, society did start to change. And it turns out that we started to deregulate, and personalisation and individualisation began to kick in. Our world began to get slightly messier than perhaps our databases could handle. But we were clever humans. We were able to take that emergent messiness in our world and constrain it into our database through patterns and practices that we developed. Now, of course, we have ambitions as humans. Our systems wanted to grow. We started to push the envelope of what we could do with those relational schemas, even those complex ones that you saw a moment ago. We've all been there, trudging through dozens of intermediate tables just to get to the data you want, and having that headache of trying to figure out how to keep queries performant and so on. And a reason for this is that relational databases simply weren't designed for the kind of data that we're working with in modern times. In fact, I would say that the relational database, despite the fact they are amazing pieces of technology, have two fundamental problems. One, join pain. That is, when you want to get information or indeed knowledge from your database, you often have to join relations together, and the mechanisms through which most databases do that are relatively expensive, particularly at scale. And the second one, something I discovered when I was at university, is this notion of accidental complexity. You can see here there is a table called customer accounts, where we as users have to tell the database how to do its job. And I can't tell you how profoundly disappointing that was to me as a student learning the relational algebra when I discovered that real databases expected me to tell it things like this, when I thought that the database should know it. Of course, what really happens on the systems that we're building is we run into these practical problems, whereby we can build a system which in which we have carefully constructed a schema, and then when we come to execute queries over that schema, we get an explosion of complexity. You've seen the schema I put on the screen a moment ago. That's an incredibly complicated schema. When we start to run queries across that schema, and particularly join-intensive queries, we get an explosion of a system. Now, fast forward slightly. In the 1990s, the web happened. Data became connected and it became globally scaled. And Tim Berners-Lee made this into a thing, the World Wide Web. And we connected our carefully designed relational databases to the web after some time, and it was great. That is until everyone else connected to the web as well. And then some of the shortcomings in our relational databases in particular were exposed. In order to address some of these shortcomings, something else started to happen. We started to talk about processing data at enormous scale. And I'm thinking here of the early pioneers in this field, the likes of Google and Amazon and so on. They wanted to process data that was much bigger than relational databases could handle. And in fact, the modeling benefits of the relational database weren't really needed either. That's a bit weird. We used to call this Google scale or web scale, and it led to organizations creating their own databases. This is quite a divergence from the norm. It would have been quite, I think, exotic for an organization, a typical enterprise organization, to decide not to buy an off-the-shelf, excellent quality relational database and instead to build their own. For example, Amazon built Dynamo for shopping carts, and Dynamo is a key value store which places an emphasis on availability, so you can always add goods to your shopping cart. Google built Bigtable for structured petabytes of data for many of their systems. And this kick-started a trend for amassing huge amounts of data. So we all latched onto this, right? Because many of us think that we'll Google, or we will be Google in the future. And of course, if Google are doing it, and Google and Amazon and all the other big web hyperscalers are smart, we should also be doing these smart things. And of course, NoSQL charged to the rescue. And we had this incredible decade, I think, of innovation, explosion in innovation around data technology. But what it really led to was a kind of bifurcated system where we made huge strides in collecting data. And in fact, the web hyperscalers we know have huge repositories of data, mostly to fuel their ML systems, and the rest of the industry has followed. But I think those of you that have been using databases in the last few years will see how easy it is relatively to just pour data into them. If you've used a system like Apache Cassandra or something like that, pouring data into your database is not hard. But how do we make use of it? How do we take data out of our warehouse, out of our lake, and so on? How do we take it to the next level? How do we begin to process that data? And the way that we've done it is to say that we are going to harvest it out of its databases and run it through some processing store. So there's now a pervasive combination, I think, of databases that store disconnected data, key volume stores, column stores, relational databases, blobs, documents, what have you. And the way that we try and garner information from that is by putting it through a processing framework, usually some high performance, highly parallel processing framework like Spark or similar. And then we invest time and energy into that in order to reify data out of this. But extracting data is hard, and it's energy intensive, and it's often not terribly responsive. Now, a long time ago, my old boss, Martin Fowler, wrote about this. He said that most data technology, he was writing in the context of NoSQL databases, but I think this applies more broadly to data at scale. They're aggregate oriented, which means it's really good when you want to store a customer document, retrieve a customer document, store a product document, retrieve a product document, and so on. But it's much less good when you want to cut across those axes, when you want to ask mixtures of questions of customers and products in particular product types for particular geographies and so on. Because it turns out data isn't always that simple. It isn't always a symmetric store retrieve, which most of the data tech handles very well. Data can be rich or poor. It can be very structured or actually unstructured. It can be uniform or irregular. And usually it's some amount of all of these at the same time. So let's demonstrate. Let's think about what we would have to do to make a simple aggregate database work. And here we can see an aggregate database. Perhaps it's a document database, and we have some people, some young people here, and you can see with your clever human eyes that some of this data is data about the entities themselves, and some of this seems to be implying some kind of linkage. So if I look at the record Jeff 1986, I can see that he's a friend of Sally DJ and Gaza, and I can see other records representing Sally DJ and Gaza. And actually at this scale it's pretty straightforward. It starts off looking nice and easy. And what we do is we reify those records out into the application layer. And we can kind of make a network or a graph, and it'd be very straightforward to see how you would do that with modern code. These would become objects in your application layer, and life is good. Except, of course, that's code that you have to test and write, but the data model is just documents, right, or just disassociated data, so that's okay, that's nice and simple. Well, to be honest, reify here, it really means compute the graph. So you're kind of really writing your own slow graph database, bit of a problem. In a graph database, it's very simple. You would just store the records and store the appropriately marked up linkage between them, because a graph database, the connected data, comes naturally in graphs. So you don't have to deal with that concern in your code. You just deal with the application concerns. But as Han Solo famously said, I've got a bad feeling about this. What happens if we do try and take our disconnected data and put it towards a connected data use case? Well, in a graph database, as you can see in the top, it's very simple to describe products that have been purchased by those people that we saw a moment earlier. In the aggregate database, in the disconnected database, it's really hard to know what to do. In this case, I've chosen to put the purchases of products in line with the usernames, with the user records, but that doesn't seem very clear. You could make an argument for having it the other way around, having the products contain a list of all of the users that have bought them, but there's no real way of understanding this because there's no idea of connectivity in the data. Only in the graph is there an idea of connectivity that can be bent towards the user's will to suit the domain that we're working in. So trying to sell products, doing something like simple social recommendations from a disconnected piece of data is actually really hard, and it then falls to our application code to make sense of it. And that's really very hard. What would you do, for example, here for a product recall or social selling? Well, I tell you, if you've got connected data, this is an O1 search operation to find out who bought a product. If you're lucky in a disconnected data set, it's an O log n compute job to find this out at high latency, which is pretty unpleasant. But as you may guess, it goes from bad to worse. What happens if you want our requirements to evolve to include those social recommendations? It's really hard in a non-graph store because you've got to compute the result over the set of data that you have, which doesn't have relationships, rather than just follow your relationships. If you remember a few slides back, we kind of gave that the euphemism reify, but really it's a lot of hard work. If you had connected store, it's easy to traverse to find the recommendations for your friends or friends of friends, or indeed to find geographic recommendations or very deep purchase history recommendations or social profile recommendations or a mixture of all of the above. Because all of this is simply traversing links in a connected model. Now, while traversal performance is critical to get performance at scale, Neo4j, the system I work on every day, does around 10 million traversals per second per core. And a traversal here is going from a record across a link to another record. On my old Intel laptop, I have no idea what it will do on this fancy new M1 that I've just recently received, but I'm pretty sure it's going to be faster. So if we're going to attain knowledge, insight, and even wisdom, we're going to need to extract more than just disconnected data floating around and being laundered through, kind of feature extraction into machine learning models. We're going to have to understand how data is contextualized, and that contextualization happens via topology or linkage. And this is what graphs provide. And processing graphs, not just disconnected data, opens up a whole new world of database analytics and machine learning that is simply not available with other approaches. Let's flip into AI ML for a moment, since I mentioned that, and it's a hot area. AI ML, the fuel is data. Now, these stats here are from Gartner. Now, I think Gartner are a relatively conservative firm of analysts. They tend to go in when something really has hit its stride for the enterprise, since that's their core market. And it seems to me that graphs and machine learning together have really hit their stride. I know this from my own experience working here at Neo4j. Our graph data science library has only been around for about a year, but it's already revolutionized graph compute. It actually came from Neo4j's algorithms library, which some of you may have used, but on steroids. And it's a system designed to do highly parallelized computations in a very RAM efficient way on top of Neo4j. Very easy to use. But graph has also been exploding in the AI research space, which itself represents significant innovation, and we know that that drives new resources. So it should be no surprise really that researchers are using graphs to improve AI, as this chart here shows. You know, in 2010 there was a few hundred papers mentioning graphs and AI, and now we're at 2020, it's like several thousand papers combining graphs and AI. And of course, this is not just graphs as in Neo4j graphs, but it's graph neural networks, graph convolutions, graph embeddings, graph learning, graph attention, graph kernel, and so on, all in this. But if you roll all of that up, we end up with this amazing stat from Gartner in 2021 that says 50% of their inquiries, that's 50% of enterprises, are inquiring about the use of AI with graph, in use of graph with their AI strategy. Now, since Gartner is very representative of the enterprise, I would say unscientifically that this means 50% of enterprises are now getting started with graphs and AI and are looking for guidance. I would also therefore guess that 25% of enterprises are already past the stage of asking Gartner for help. And 25% of enterprises therefore are probably lagging. So now as we start 2022, one cohort is in potential danger of being left behind by the people at this conference, whereas graphs will empower the others. Now at Neo4j, as I mentioned, we have an incredible solution for dealing with graph compute. It's called the Graph Data Science Library, and it is a very thorough library that consists of a broad set of unsupervised and supervised algorithms for graph analytics and machine learning. If you want to find, for example, links between nodes in a graph at scale, or want to find how important a particular node is or a particular path is in a graph, or detect communities of practice if you're looking for perhaps fraudsters in a community, or if you want to predict how a graph might evolve or how similar nodes are in a graph, we have all of this covered. Finally, we also even have graph embedding, so you're able to take the entire topology of your graph and turn it into a feature for a machine learning model to train on. All of this is accessible right out of the box on Neo4j. These are just single procedure calls from the Cypher language, so it's by far the easiest tool to use in the industry, I believe. And the way that we see this in Neo4j is that first you organize your data into a graph, into a knowledge graph. And it's the same graph that you'll be used to if you're using Neo4j as a transactional database. You've got customer bought product and that kind of thing, and that gives you an organizing principle for your graph. On top of that, you can then let the database do some of the heavy lifting for you using unsupervised techniques and graph algorithms. Ask the database to find you clusters, neighborhoods, busy paths, important nodes, and so on for you. And then at the top of this kind of hierarchy of learning, you can use graph native machine learning, where we're asking the infrastructure itself to encode the topology of the graph in a format that is suitable for machine learning without human intervention. I think that 2022 is going to be the year of graph native machine learning. Neo4j supports embeddings, which are these non-human readable topology encodings, and they make for superior features and better predictive models. Of course, we can't do any of this unless the underlying database is fit for purpose, and I'm very pleased to say that Gartner agrees with this. So using graph techniques at scale will form the foundation of modern data and analytics. Let's go back to my home turf and see what's happening then in the world of graph data management. So in the 17th of June last year, 2021, at the Nodes Developer Conference, that's the Neo4j Online Developer Summit, my boss, the Neo4j CEO, Emile Frem, demonstrated a 1 trillion scale graph. that is 1 trillion relationships in a graph running at near constant latency as both load and volume increase. This was based on an idea by the LDBC, the Linked Data Benchmark Council, who have a social benchmark. We had a look at that benchmark and it gave us an idea for a demonstration about how you might use graph in the future. So we saw this and we decided that we would build a small database. This has got 11 shards and it deals with about 29 billion operations a second. So far, so good. But we can take that a step further. We'll scale it up to 100 shards. And now we have 100 billion relationships in this. And notice that the response time, even though there's much more infrastructure, much more data here, and much more load, the response time for a query is still around 60 milliseconds. And if we scale it all the way up to actually past 1 trillion nodes, 1,129 shards here, still at around 60 milliseconds average query latency. So you can see that as your needs grow, as your use grows, the database underneath your clever connected data applications will grow with it. Now look, this isn't something that everyone needs. Not everyone has 1 trillion nodes. But if and when you need it, Neo4j's got you covered. And that comes on the back of, I think, an incredibly important year in terms of investment in the space. Neo4j itself took on $400 million worth of investment, including from Patrick Pichette, who was Twitter's ex-chairperson, who joined our board and our investors. And this investment goes directly into improving the technology that supports connected over merely collected data. And it's a huge investment. I think it also shows that graphs aren't niche. Graphs are here, they're mainstream. Neo4j is the mature global player in the industry. We lead and others try to follow. And Neo4j's technology and the solution offerings accelerate because of this investment. We have more engineers and more innovation, and we can help you get more stuff done. For the whole graph industry, zooming out of just Neo4j, I think there's around $500 million of investment in the space. That's my guess. Not even including the cloud hyperscalers, Ali, Tencent, Huawei, Microsoft, Google, Amazon, who are all investing. Connecting, I believe, will outpace merely collecting based on these trends. And in 2022, I want to draw your attention to a couple of ways that you can start connecting data and getting value from connected data and not just collecting it. You have access to our free cloud services, as well as being able to install, of course, Neo4j on your own laptops and desktops. We have AutoDB, which has a free tier that's available right now on AWS and Google Cloud in over 45 cloud regions. Other clouds are coming soon. Free tier available with a couple of clicks, which gives you the ability to store and query graphs. Complementary to that, we have AuraDS, Aura Data Science. EAP is available at the moment. You can sign in for that. And that's the power of the Graph Data Science Library on the cloud for free for you to use. I think these set the state for the future of the graph, for the future of connected data, not just collected data. It's a service that allows you to store and query your graphs humanely at scale, and a service that allows you to analyze, train ML models, make predictions alongside that stored connected data, also at scale. And since it's just a couple of clicks, it's very simple to set up. I would encourage you to take a look. So if that's got you interested, let me point you at a few resources that you might use. Neo4j has a bunch of books that you can get for free. If you go to the Neo4j website, you can download the O'Reilly books and the For Dummies books for free from us. I would also point you to the Graph Algorithms for Data Science and Graph-Powered Machine Learning books made by friends of mine and Neo4j employees and Neo4j partners. They're amazing. There's also a lot of material on the Neo4j YouTube channel, and I think the friendliest, most helpful community on the planet at community.neo4j.com. So look, I'm slightly over my allotted time. I do apologize, but I hope I've shown you that the tantalizing power of connected data is an absolute powerful proposition compared to just having a big heap of rotting disconnected bits. Graphs are amazing, and I'd love to hear from you what you're doing in 2022, so do please stay in touch. Enjoy the rest of the conference, and if you want to talk graphs with me, my contact details are on there. I'd look forward to hearing from you. Thank you very much.